Hello, my name is Paul Roberts, and I'm the before nCode DesignLife and nCode GlyphWorks. And today I'm going to be presenting one a series of webinars, and this today is on what's new in nCode 11.1. This is a point release adding some functionality to 11 that we released 2 or 3 weeks ago. So the main areas we've focused on in this release are addition of some new capabilities. So where we're adding some functionality to some of the current available glyphs or processes, we've added some new capabilities to some of those. We've also looked at increasing performance in some of the processes, as I'll mention a bit later, and also adding some new technologies. So actually adding some new things, new capabilities, new technology functions that weren't in there at all. And this theme we've got throughout 11.1 continues. The theme for 11 was more in the vibration area and concentrating on the CAE area. And in 11.1 we've concentrated again on vibration, but now more in the test-based area and data cleaning. That's the major themes running through the release. Just a quick summary of the products we're looking at. So the 3 main products that nCode supply are nCode DesignLife, you see on the left. So this is for CAE-based analysis, so where you've got results from an FE analysis and you're looking to do some post-processing on that in terms of fatigue calculation, encapsulating that process in a flow and then being able to use that. Very scalable analysis process and very configurable. In the center you see nCode GlyphWorks, so this is more based on test data, so where you've got measured things like strain gauges, GPS data, CAN bus data, where you're measuring that from some vehicle or some application, and then we're doing analysis based on that. So that's not only in the fatigue area, but also in terms of NVH measurements, frequency, and generalized analysis of that data. And on the right you see nCode automation. So we won't actually be talking about automation today, but this is a way of automating your processes and getting web access to those results and the database of all your analysis results and automating the entire process. That we won't be covering today. We will be covering DesignLife and GlyphWorks. And I'll start with GlyphWorks. So as I said, work in the test-based area. So here you have measured test data, NVH type data, GPS data, CAN bus data, any you want in terms of what's been measured. And this is a summary of what is in 11.1, the new things in there. So I'll be covering these a bit more in detail as we go through the slides, but this is starting off with the data cleaning option we've added. So this is in addition to the tools we already have in the frequency and time-based domain for looking at noisy data. So we've added a Wavelet denoising glyph. So to look at things within the Wavelet domain. We've added a Kalman filtering glyph, which I'll cover in a bit more detail, and also to go with that a worked example of how to use that. We've added the Kepler analysis type to the frequency spectrum glyph, so this is another spectrum type to go along with PSD and amplitude spectrum. We've added a new glyph within the frequency package called Hilbert transform. I'll cover what that's useful for in a bit more detail. We've also done several display improvements, quite a lot of work on different display glyphs, which I'll cover in a bit more detail. And we've added one new supported data file format, the in-test CSV file format, which is a formatted CSV file, and also the ability to write the RPC floating point format. We've read and written the initial format that was around for a long while, the binary format, but the integer format. I'm sorry, but we also read the floating point format. Now we actually write that out as well. So now I'll go through those in a bit more detail. So first, the data cleaning option. So obviously, getting good data is reliable data is still a challenge. There are lots of things that can cause noise with data, and we need to remove that in some cases. The Wavelet denoising glyph basically decomposes the signal you've got in the time domain into a combined frequency and time domain called the Wavelet domain. This allows you to do some things that are more difficult to do in either the frequency or the time domain. And one of the major applications for this is removing Gaussian type noise on a signal. So if you've got random Gaussian noise on your signal, the Wavelet denoising glyph has 2 or 3 options within that to allow you to remove that noise. It also can be used for things like classifying your signal. So if you've got transient noise examples, for example, like in a door slam test, you can use the decomposed wavelets to give you some form of analysis to that to classify the noise type, and so you can do more detailed analysis of that in the wavelet domain. So that's one new glyph within the data cleaning option. The second new glyph is the Kalman filter glyph. So basically this takes account of noise in a signal by combining the noisy measured data with a physics model of the process that data is measuring. So the simplest thing to explain, for example, is like a GPS trace where you're measuring latitude and longitude. And from the physics model, you can define what is possible for a vehicle, knowing its current speed and direction, where it's likely to be next in the next point in time. So that gives you a calculation of where you think you should be, and you can compare that with where the measured data says it is. And using a weighted average of those 2 positions, you can come up with a more accurate measurement of where the data should actually be. So one of the major applications for that is in cleaning up the GPS data. And in fact, the Kalman filtering is used pretty much universally in most standard GPS devices internally to help clean that signal. It also can be used in a similar case for cleaning up noisy data for control systems. So if you're measuring data in an automotive control system, for example, that's got noise on it, and you've got some measure of what that physical process is, you can use that to clean that data up. So typically using things like engine run-up tests, where you know you might get noisy data from the engine run-up, but you know how fast the engine can go and how fast it can accelerate. So that can give you some appreciation of what is possible. I'll run through both of these with some worked examples in a second, so you can see exactly how they're used. In addition to the Kalman filter glyph, we've also added a new worked example on Kalman filtering. There's some complication in actually how you format a physical model of that component. So the worked example takes you through step by step about and how you can derive that model to use within the Kalman filter. So that is a new option, the data cleaning option with those 2 glyphs. We've also added Kepstrom analysis within the frequency spectrum glyph. So this is a new analysis, new spectrum type. And basically this is used to try and calculate the more fundamental frequency of a process, and helps to estimate the amount of periodicity. So if you've got a process with sidebands on top of that, it will pull out the more fundamental frequency and draw more attention to that and minimize the other peaks that are associated with harmonics. So this allows you to get, from a complicated signal, allows you to more zone in on what the fundamental frequency is. And it's particularly useful in data with repeated patterns in the spectrum. So for instance, differentiating faults within gearboxes. So one of the major applications is in gearbox analysis and machine diagnostics. So in a gearbox analysis, you will have lots of fundamental frequencies associated with different gear trains. You will have sidebands of all those frequencies, and the Kepstrom analysis allows you to more easily isolate those. That can then, within gearbox analysis, can then be used to see what changes may have happened in that process. So you can use it for condition monitoring, for example, if you've got lots of different measurements throughout the life of the gearbox, because you're picking out the fundamental frequencies and the level of that. Any change in the condition of the gearbox caused by cracking or wearing of the gear teeth will cause a change in this, and the Kepstrom analysis is one of the techniques that will accentuate that and let you pick that up more easily. In a similar vein, the Hilbert transform glyph can be used in a very similar way. Basically, this glyph, it calculates an analytical signal which allows you to represent that your measure signal in a complex form. So it's especially attractive as properties for looking at signal processing. The 2 major options within that glyph are to calculate an envelope of the time signal you've given it, or to look at the phase between adjacent points, so in effect the instantaneous frequency output as a train of pulses. So the first of those, the envelope function, this is particularly useful for determining the dampening or decay rate of a resonant process, say from an impulse response function. So if you measure a hammer test, for example, on a component, you can use the Hilbert transform and generate an envelope of that decaying process and then use that to calculate the damping. Similar way you can use to investigate the propagation time from a cross-correlation function. So if you've got two signals, you can run a cross-correlation function between those two and use the envelope function to generate the propagation time between those two signals. And again, like the Kepler analysis, particularly useful for bearing fault diagnosis. So again, run the envelope function, you can then look at the statistics of the envelope function and use the statistics of that function to see whether your condition has changed between a series of measurements. And I'll show you an example of that when we go to the examples. The second function of the Hilbert transform glyph is to generate a train of pulses which are give you the instantaneous frequency. So this, if you use this combination with a pulse to speed glyph, we allow you to calculate a frequency versus time signal, which you can also get with the with one of our other glyphs within the frequency domain, but this will give you an instantaneous measurement as opposed to an averaged over a buffer, which you are doing with the FFT type process. But give you a similar result, but a more instantaneous frequency at any point. So that's the main glyphs that have been added at 11.1 in GlyphWorks. If we look at some of the other improvements that have been added, we've done quite a lot of work on the displays. So these are some of the major things that have gone in, amongst others. So in the XY display glyph, we now allow the X-axis definition to be defined on a per channel basis in terms of metadata limits. So you can automatically zoom to different sections to overlay different sections of data. Also, the number of axes on an overlay plot can now be user defined. So it used to be either one or all of a separate axis. Now you can define the number of axes you want and apply the different number of channels to different axes. And the legend now indicates in a better way which axis is relevant to which channel. We've also added some annotations. The XY display glyph has always been able to add annotations to the plot, but we've added that functionality also to the waterfall display glyph, so you can add text and shape annotations to that plot. In terms of the XY display glyph, that's associated with the data position, and but in terms of the waterfall displays, it's associated with a position on the screen. And we've also added quite a lot of functionality to the nCode viewer. So now, optionally, you can add the full legend to the XY display in the nCode viewer. So if you've got more complicated metadata you want to view in the full legend, you can add that, so you can get a more complex view. Also, when there's a license available, you can also now save and load configurations files for various different display types. So for example, if you want a particular setup you want for a display for a particular plot type, for a particular type of data, you can save that configuration. When you pull that data back into viewer, you can also pull the configuration back in, and then you can more easily get back to the view type you want for that particular data. So it just helps you get back to prepared views you've already used. Some other enhancements, quite a lot of these in the vibration area again. So in terms of integration and differentiation, they've always done that within the time domain. But now that can be carried out directly in the frequency domain based upon the frequency results in histogram data format. So you can differentiate or double differentiate, and the same with integration directly in the frequency domain within either of those glyphs. We've taken some restriction from the materials input glyph. Basically, this allows you to pull materials data in from a database and pass it out on a pipe, so that you can use that directly in any flow process. That was restricted to a fixed set of material types. So that, but now that's been expanded, so any material type, including custom types derived by the customer, can now be output. So they will generally be output in terms of all the metadata from the material, and in some cases where you've got arrays of results, they will also be output as multi-column. So this allows you to get access to any material types you may have defined yourselves as custom materials directly within a flow, to use those directly. The MATLAB scripting glyph has been updated. This now has support for complex frequency input and output. This was on the Python glyph in the past, but not on the MATLAB version, so this has been added at this release. We've now also gone to the latest release of 2015 of MATLAB. So a small increase in functionality in the MATLAB glyph. And continuing the theme of vibration in the units conversion glyph, when using histogram data, we've added a new option that allows conversion between different spectrum types. So you can go between power spectra and amplitude spectra within the units conversion glyph without having to rerun the analysis. Okay, so that's finished the updates within GlyphWorks. So I'll just jump out for a minute now and show some examples of how those are used. So if I start off with wavelet analysis. So we have one new glyph, wavelet denoising. Within that glyph, in denoising mode, we have some functions for whether you are low, high signal to noise ratio, data, what the factor of multiples of the standard deviation is that you're removing. So it allows you some measure of how much noise you want to remove. And then internally this will decompose the data into the wavelet domain, apply these thresholds in order to remove the noise, and then give you the result still in the time domain. So this particular data, for example, has got a 50 Hertz noise on that signal. We can use that to remove this. You look at the frequency response to that data, you can see that the 50 Hertz is completely removed. You will notice it hasn't removed some of the other problems with that data. In this particular mode, it's really just from removing Gaussian type noise. We can also then work on that data in the wavelet domain. So at this point, we have a decompose option. So we can decompose the signal into the wavelet domain. When we run this process now, we get a set of wavelet functions. So this is the individual wavelet levels from the data. And at that point, you can do analysis on those. So in this case, I'm running a spike detect, and I'm taking the spikes out in the wavelet domain. Then I'm zeroing some of the data out, and then I'm using the second wavelet domain in reconstruct mode. So what this does, it looks for a set of channels with the appropriate metadata telling it that these are wavelet levels. It will take those automatically then and reconstruct that data. So at this point, we've taken out the wavelet function that gave you the drift on this signal, and also some of the spikes in the wavelet domain, and still maintaining the signal in terms of the good signal you want. And this gives you the much greater functionality at this point. Because you're working in the wavelet domain, you can take out some noise functions that are not available to be edited within either the time or the frequency domain. So it really extends what you can do in terms of removing noise. It's probably not applicable to most sort of normal spike detection and normal filtering that would be applicable to most data. So if you've got normal data where you know the frequency content and you can take that out with a filter, that's still more appropriate to do. And it's still appropriate to take out most spikes within the time domain. But this gives you some extra functionality in data where you couldn't remove the noise problems in that way. So that's a wavelet example. We look at, oh, no, not that one. We look at Kalman filtering. So this is basically I'm showing you the worked example data. So we have time series input. We have a multi-column input. In this case, this is a physics model. So this is data that define a set of matrices that define what the model is. So these define the mapping between the input and output data and the calculation formula between the input and output. and then also some noise measurements. So this is the measurement of the noise on the calculated signal, measurement of noise on the measured signal, and some initial values for this trace. And in this example, it's a very good engineering example of a cannonball flight. So this is basically the trace of the x-axis and the y-axis of a cannonball going through the air with an overlaid noise signal. So the physics model in this case is just the equations of motion for a body as it flies through the air, so affected by gravity in terms of the one axis and then not in the other axis. So if I run this process, this then combines that physics model with the noisy data measurement and then gets you a clean signal in terms of the trace. You will find at the beginning it takes some time to work out where the real data is. Once it gets that, so the physics model is then okay compared to the measured data, it will give you a very good trace. And so this is used universally pretty much in GPS devices and was first developed and used in that method for NASA for their Apollo lander and Apollo missions, where they needed some cleaned up GPS data and they needed to do it based on an easy process to implement. So the two things I said with that is we look at Kepstrom and Hilbert. So the Hilbert transform. So this is an example of a process where we're looking at condition monitoring. So these are a set of measurements from, in this case, a gearbox. So we have noise measurements from a particular position in a gearbox. We're doing some process to add these together, and then we're using the Hilbert transform in the center just to develop the envelope function. So all this is doing, develop an envelope function and then looking at the kurtosis of the envelope function as it goes through the data. And then this is showing you the variation between the data as it goes through. And in this case, it's just looking for changes because it's looking for the monitoring the condition and whether it changes. It's not looking for any real levels in that data. It's looking for whether that kurtosis changes significantly as it goes through, as it does in the final measurement where you get much higher when it's after the Hilbert transform. So it's basically using it within a process to get you an envelope function to use that to get some other results. In a similar way, you can, as I mentioned, you can also use it for looking at the decay of a signal and looking at the damping. This is a measured set of data where we've got single degree of freedom system with a damp system, so you're getting decay of that signal. Now, if you've got enough resolution, you can, in the frequency domain, look at this and find the damping out by finding the 3 dB drop-off point, and that will give you some measure of the damping to the peak. But that, if I run this process, the accuracy you can get on that process is defined by how accurate your PSD is. So you have some resolution issues with the PSD compared based on what the sample rate and the frequency resolution you want is. Whereas once you develop an Hilbert transform, the Hilbert transform is just doing the envelope function again. That gives you this envelope function if you switch this back to linear mode. So basically that is the envelope of the decaying signal. Because it's a single degree of freedom system, if you put that in log on that axis, you will get a straight line. All I'm then doing is pulling off 2 points on that straight line. That gives us the data for the drop-off at that point and the frequency step. And then you can use that directly to measure the damping ratio and also the decay rate of that signal. So that you can get the Q factor for that, and then that can be used in any measurements or future calculations you need the damping for. So quite a good use for that envelope function. Although you can do that from the frequency domain, it gives you a much more accurate answer. I also mentioned we'd added Kepstrom analysis. So this is a similar process to the one I showed with Hilbert. So there again we have a set of measurement data. Again, looking at a different gearbox in this case, but still gearbox vibration measurement. And within the frequency spectrum, we're now doing the Kepstrom. So this is where you normally get power or energy or amplitude spectrum change that to Kepstrom. That in effect is doing a FFT of the log of the FFT. So basically accentuating anything in the FFT to pull out the fundamental frequencies in that data. That then allows you to do some comparisons between before and after that data. Again, in this case, looking at condition monitoring and seeing whether there's any changes in that Kepstrom plot after you've got through some damage. So looking for in this case, wear in the gear train and how that changes the signal. So quite useful for condition monitoring. Okay, so that covers most of the things that we've added to GlyphWorks. If I now move on to look at DesignLife. So as I said earlier, DesignLife is the analysis tool we use within the CAE environment. So in effect, post-processing stress, force results from FE to look at damage calculations in that area. We added quite a lot at version 11 in terms of functionality in DesignLife, and this release we concentrate more on GlyphWorks. So a few less improvements within DesignLife. But what we've added is some speed and capacity improvements. We had some internal limits which, although we're in the sort of billion count of result entities, even that with large models today with millions of elements, when you use critical plane that gives you multiple results, and maybe duty cycle that give you multiple results for each duty cycle location, and node and element results where you have multiple results for each node, you can get to quite large data arrays that are available. And we've taken all those internal size limits away, so we shouldn't be eating any of those size limits for quite a long while now. And also improve the speed on some of the modeling within the vibration area as well. We've also had some improvements for material validation, which I'll show you in a minute. So this is basically when we first try and run a job, we will validate the job to see whether it's possible to run it. We will check all the materials are available and whether they're mapped correctly to the materials database. And if you're running a very long, big job on a big model from a bill of materials, this might be hundreds of different materials you're mapping. And unfortunately, before we just told you that if any of them were wrong, we just told you the first one that was wrong. Now we will list all of the ones that are mapped incorrectly, so you can then go and immediately go and fix them all at the same time. Over the last few iterations, we have been adding quite a lot of capability in the composite area. So we now have 2 different engines for calculating short fiber composites, and we've added support to those for layered solid elements for that analysis. Up until now, we've done layered shell elements and individual solid elements. We've now added the capability of the layered solid elements. We've also added some extra output to the Dang-Van, well, not just for spot weld, but for the complete Dang-Van engine. So when you're calculating a safety factor on the Dang-Van analysis, you can also output the maximum von Mises stress that also occurred at that point. Just a way of looking a bit more carefully at the stress at that point. And also, we've changed a little the standard processes within GlyphWorks. I'll show you this in a second in a quick demonstration, but we've also always had on the left-hand file menu, you'll see in the picture at the bottom, a set of standard processes for GlyphWorks. And we've now added the functionality to add multiple sections to that, and we've added initially 9 DesignLife processes. So that range from standard time series for EN and SN to vibration to a DesignLife post-processing to post-process results within DesignLife. So just break out again a quick demonstration of a couple of those examples. So a quick look at the materials. So when you try and run one of these analysis jobs now, I've deliberately got 3 materials that are now not allocated properly. So now you'll get a result telling you exactly which materials, and the detailed error plot will give you a list of each one individually, so you can go to those and fix which were wrong. And if you've got lots of them that are wrong, we basically tell you the number. So now you get told there's 101 material groups, and we will list the first 100. So we haven't gone and listed them all because there might be thousands. So we've gone through and told you there's 101. and listed the first 100. Quick look at standard processes as well. So these are the GlyphWorks standard processes. We will be adding some more of those at 12, but these are the ones that were in there at 11 at the moment. And now we've added these extra ones in terms of DesignLife standard processes. So we look, for example, at the DesignLife post-processing. So this is a post-processing example where I can pull an FE model in, and I can pull some previous analysis results in, and I can reanalyze those results on the FE plot, and also look at hotspot detection as well if you're interested, if you want to know where the worst damage points are. So it allows you to post-process results and get those results back in easily to the post-processor. Okay, so that covers the things we've added to DesignLife. So in summary, a major theme throughout this point release was looking at vibration area and data cleaning, so adding some more functionality in the data cleaning area and some functionality throughout a lot of the glyphs included in the vibration area. That included some new capabilities, so adding Kepstrom analysis, for example, within the frequency spectrum glyph. Also some improved performance, particularly in the DesignLife area, taking out some limits in terms of model sizes. And also looking at new technologies where we've added Wavelet, for example, Wavelet, Hilbert, and Kalman filtering, all new technologies to the software. Okay, so that concludes my